Welcome. In the last module what we have seen? We have seen ideal op amp, and ideal op amp has few characteristics such as infinite voltage gain, infinite input impedance, 0 output impedance, infinitely fast. Of course, op amp has two golden rules. We have discussed those golden rules. First is that the input to the op amp draws no current, and second is the output will do whatever it can to make the voltage difference between two inputs 0. These are the two golden rules. The ideal versus real op amp, right. Real is nothing but actual or practical op amps, and we see that there is a difference in terms of the character parameters, where we say voltage gain is infinite, actually it is about 10⁵ to 10⁹. When we talk about gain bandwidth product is infinite, it is about 1 to 20 megahertz. Input resistance infinite, in actual case it is 10⁶ to 10⁻12 ohms, while output resistance is 0, in actual or real case it is about 100 to 1000 ohms. Then we have seen balanced unbalanced power supplies, right, and we have seen single ended output and double ended output. I will just skip this fast just to make sure that the balanced and unbalanced power supplies are used in several applications. Most of the application you will see balanced power supply, while some applications also used unbalanced power supply. Same way single ended output is with respect to ground, double ended output it is not with respect to ground, that is why it is also called floating output. Then we move further and we see that the internal op amp formula is nothing but V out equals to gain into V plus minus V minus, is inverting minus non inverting or non inverting minus inverting. Whatever is great, like whatever is higher, the signal at inverting is higher, right, compared to non inverting, then our output will be negative. If the signal at non inverting terminal is higher compared to inverting, our output will be positive, right. Then we have seen feedback, negative feedback, and negative feedback is used for amplifiers, while positive feedback is used for oscillators, right. So, we have seen that what are negative feedbacks, what are positive feedback, right. Then we have seen the internal stages of operational amplifier. It consists of differential amplifier, intermediate state, level shifter state, output stage, and most of the op amps are now replaced by MOSFETs. The internal circuit that you see here BJT, most of the cases now we are using MOSFETs, all right. Then these are very important parameters or characteristics of the operational amplifier, starting with open loop gain, right. What is open loop gain? It is a voltage gain of operational amplifier when no feedback is applied. So, practically it should be or it is several thousands. Second is input impedance, it is finite and typically greater than 1 mega ohm, but for FETs for the input state it can be increased to several 100 mega ohms. Output impedance around 1 to 2 ohm. Bandwidth of practical op amp in open loop is very small, but by using negative feedback we can increase the bandwidth to desired value. Input offset voltage, when both input terminals are grounded the output should be 0, but when you do that, like I said in the last course, that when you ground both the input terminals of the operational amplifier you will not find that output voltage is 0, right. And to make that output voltage 0, a small voltage is required to apply to one of the input terminals, and that small voltage is nothing but your DC offset voltage, is called input offset voltage. Same way if you talk about input bias current, what is input bias current? If you come back on the screen, for ideal operational amplifier no current flows into the input terminals, right. So, but for practical op amps you will see that the input currents are very small, around 10⁻⁶ to 10⁻14 ampere, right. So, the input terminals which are the base terminals of two transistors do not current small DC current. This small base current of transistors are nothing but the bias currents denoted by IB1 and IB2. You see why this happens? Because the two transistors of the differential amplifier. So, when we see most of the op amps are used as a differential amplifier, right, differential amplifier for the input voltage. The two transistors of differential amplifier must be biased correctly, but practically it is impossible or it is not possible to get exact matching of two transistors, right. This mismatch of the two transistors will allow a small base current to flow or small DC current to flow to the input of the transistor, right. This small base currents of the transistors are nothing but input bias currents, right, bias currents denoted by IB1 and IB2. So, how input bias current is measured? The input bias current is measured by using this formula, where IB equals to mode of IB1 plus mode of IB2 by 2. Where we talk about input offset current, it is the difference in the magnitudes of input bias currents, right. IB1 and IB2 is called input offset current and is denoted by IOS equals to mode of IB1 minus IB2, right. One very important point that you have to remember here is that both input bias and offset current depends on the temperature. If you change the temperature, you will find that the input bias and offset current also changes. Zero input current, right. What is that? The current drawn by either of the input terminals is 0, right. In reality, the current drawn by the input terminal is very small, of order of micro ampere or nano ampere. Hence, the assumption of 0 current is realistic. These are all realistic simplifying assumptions, right. So, actually ideally what will happen, that the current drawn by input terminal should be 0, but practically when we measure it, it is about micro ampere to nano ampere, which is close to 0. Hence, 0 assumption is realistic. Second is virtual ground, very important in case of operational amplifier. So, this means the differential voltage Vd between the non inverting and inverting terminals is essentially 0, correct, essentially 0. This is obvious because even if the input voltage is few volts, due to large open loop gain of the operational amplifier, the difference voltage at the input terminal is almost 0. We have seen that, right. So, let us move forward. We have seen the concept of virtual ground, right. So, even if one of the terminal is grounded, the second terminal is also considered as a ground, and that is a concept of virtual ground. Then we have seen differential mode gain. Differential mode gain is nothing but VO or output voltage equals to differential gain into difference of input voltages V1 minus V2, right. So, AD is nothing but gain with which differential amplifiers amplifies the difference between two input signals. Hence, it is also called differential gain because it amplifies the difference between two input signals, right. Common mode gain, what does common mode gain means? So, it is a factor by which common mode input voltage is amplified by operational amplifier. So, what exactly common mode gain means? If we apply two input voltage which are equal in all respect to differential amplifier, right, that means let us say the voltage at the inverting terminal we consider V1, voltage at non-inverting terminal of the op amp we consider V2, and if V1 equals to V2, then ideally what should be the output? Output voltage should be VO equals to differential gain into V1 minus V2, V1 is equal to V2. So, output voltage should be 0, output voltage should be 0, but in practical op amps, practical differential amplifier, right, it does not only depends on difference voltage, but also depends on the average common level of two inputs, and such an average level of two input signal is called common mode signal denoted by Vc or VCM, and this VCM can be found by formula VCM equals to V1 plus V2 by 2. Right. Thus, we cannot just say that VO equals to AD into V1 minus V2, but the output voltage of the operational amplifier depends on AD V1 minus V2 or AD into VD. V1 minus V2 is what? VD, right, differential voltage. So, AD into VD plus ACM into VCM, right. So, the output voltage depends not only on the differential mode gain, but also on common mode gain and common mode voltage as well as differential mode voltage. So, then we have seen common mode rejection ratio. So, what exactly common mode rejection ratio means? Right? Common mode rejection ratio is the ratio of differential gain to common mode gain. Ideally, the common mode voltage gain is 0, right, because we do not want common mode gain, we want only differential gain. But So, in ideal situation, if we say that common mode gain is 0, then what will be CMRR? CMRR would be AD by 0, which will be equal to infinite, right. The CMRR ideally should be infinite, but practically you will see that AD is large and ACM is small, hence CMRR is also very large. And many times you will also see that CMRR is expressed in decibels. Now, input offset voltage we already discussed, right, input offset current, right, the algebraic difference. What is the technique to null the output voltage? Technique to null the output voltage. You see, when we short the input terminals 2 and 3 to ground, right, practically it should be 0, output voltage should be 0, right. So, but it is not 0. So, we have to make it 0, that is called nulling output voltage. So, we have to connect a potentiometer between compensation pins, right, 1 and 5. I told you earlier 1 and 5 are the compensation pins, right, and with a wiper to VEE. So, potentiometer, with the help of potentiometer we can adjust the output voltage VO to be 0, right. So, we turn the potentiometer such that we apply a small amount of voltage which is called offset voltage to make our output voltage 0 or to nullify the output voltage. Now, we then found that the input bias currents affect the amplifier operation, right, and we took an example of how the input bias currents IB1 and IB2 affect the operation, all right. So, we will just skip this, you can just look at my earlier course, right, and look how exactly the input bias currents IB1 and IB2 affects the operational amplifier or amplifier operation. Then we also saw how we can compensate the effect due to the bias currents, right, and what resistance can be used to compensate the effect of bias current, right. So, again you see the videos that are already available, and when you see that you see those videos, you will understand how we can compensate or how we can exactly compensate the effect of the bias currents. Then if you come back to the screen, what we see, another question is how does input offset voltage or how does input offset voltage affect the amplifier operation, right. Earlier it was input bias current, here it is input offset voltage, right. So, this also we have seen. So, just look at the videos please, right. Then the next example is thermal drift, right. These are all datasheet parameters, by the way, these are all datasheet parameters, right, datasheet parameters. So, when you see input offset current, input bias current, input offset voltage, CMRR, these are all datasheet parameters. Okay. So, just look at it, thermal drift, right. Being semiconductor devices, op amps are subject to a slight changes in behavior which change in operation of the temperature or which change in operating temperature. So, if the temperature changes because it is semiconductors, right, the op amps are subject to slight changes. What behavior changes are there? A circuit nulled at 25 degree may not remain so when temperature is rises to 35 degree. So, if there is a temperature difference of 10 degree, then you will see there is a drift, and this is called, of course, this is called a drift, and bias current, offset current and offset voltage change with temperature, right. So, thermal drift is very important parameter, we need to understand. Thermal drift parameters can be specified for bias currents, offset voltage. The manufacturer data sheet specifies the quantity of any particular op amp. It tells about the amount of input offset changes with each degree Celsius change in temperature. So, for example, if you take LM741A, the worst case drift is 15 microvolts per degree centigrade. So, if the circuit has to operate from 0 to 60 degree, the input offset voltage, right, or input offset could change by 15 microvolts per degree centigrade into 60 degree, which is 0.9 millivolts over 60 degree temperature change, which is really huge change, right, 0.9 millivolts. So, let us take an example and let us see a non-inverting amplifier with a gain of 100 is null at 25 degree. Okay. What will happen to output voltage if the temperature rises to 50 degree centigrade? So, from 25 we go to 50 degree centigrade, and for an offset voltage drift of 0.15 millivolts per degree centigrade, right. So, in this case it is very simple, we can write the input offset voltage due to temperature rise is nothing but 0.15 millivolts per degree centigrade, right, into 50 minus 25 is equal to 3.75 millivolts. Since this is an input change, the output voltage will change by VO equals to VOS into ACL, or 3.75 into 100, gain of 100, right, 375 millivolts, right, 375 millivolts. This is a huge change or major shift in the output voltage. Thus, it is very important to understand the thermal drift, and based on the thermal drift, based at different temperature, you have to nullify your op amp, or you should understand the temperature compensation circuits. So, other parameters: input resistance, input voltage range, large signal voltage gain, output voltage swing, right. These are the parameters you will see in the data sheet. So, impedance in looking into input pins, LM741 has a minimum input impedance of 2 mega ohms. Many op amps have input impedance of or over 1 giga ohms, alright. Input voltage range, how high or low voltage at the input pins can be applied before op amp does not function properly. Practically we know that if there is plus minus 15 volt supplies, the input should stay below plus minus 13 volt. Large signal voltage gain, what is that? The gain of op amp at DC, that is low frequency, right. Earlier we stated that the gain was infinite, we always see that the gain is infinite, right, but in real situation it is large but not infinite. The typical gain is about 200 volts per millivolt or 200,000, right. Many op amps have gain of greater than 10 raised to 6. Output voltage swing, what is that? The output can swing all the way to power rails, right. It cannot go all the way to plus minus 15, but the maximum output voltage also depends on the load current. With a smaller load, the output can go higher than with a larger load. It is obvious, right. Most op amps can swing to the output to within a few volts of power rails, right. These are the special op amps called rail to rail op amps that can swing the output to within 100 millivolts of the supply rails. It goes as close as to 100 millivolts of the supply rails. So, if it is plus minus 15 volts, it can go 14.9 volts, alright. So, these special op amps use battery products which power supply may be 6 volts or less. So, we have to see how much voltage we are applying. Then there is a output short circuit current. What is that? How much current the output can source or sink from the output pin is the output short circuit current, right. The output voltage will drop near 0 volts when delivering the maximum current. Typically, the op amp cannot deliver more than 25 milliampere. Then we have seen common mode rejection ratio. There is another parameter in the data sheet. What is this parameter? The ratio of the difference gain to the common mode gain. We have seen that, right. AD by ACM, and CMRR should be extremely high. CMRR should be extremely high. So, if you talk about 741, that is LM741, the worst case scenario for CMRR in LM741 is 7 dB, while and typically about 90 dB, right. Some instrumentation and differential amplifier can have a CMRR over 110 dB, that is about 300,000, very high CMRR, excellent for the operation amplifier to be used as an amplifying circuit. Power supply voltage rejection ratio, PSRR, this is another parameter. Then when you open a data sheet, you will see PSRR. So, what is that? This tells about how well the op amp filters out the noise coming from the power pins, right. So, noise can be generated from the power pins, how well it can be filtered out. So, using a 12 volt supply with 100 millivolts of ripple of at 120 hertz, how will this affect the op amp circuit? Let us take an example where we are using a 12 volt supply, right, and there is a 100 millivolt of ripple at 120 hertz. In this case, with a PSRR of 96 dB, the ripple seen by the input will reduced by a factor of 63,000. So, with a 100 millivolt ripple and PSRR of 96 dB, the op amp inputs would see a ripple of 1.6 microvolt. For a gain of 100, the output will have a ripple of 160 microvolts. Even when there is no input of the op amp, this is why it is required to filter the power supply and to have a good PSRR. You understand? See, if we have this example where 12 volt power supply is there and about 100 millivolt of ripple is there at 120 hertz, right, then with a PSRR of 96 dB, right, PSRR of 96 dB, if we consider the output would see about 160 microvolt of ripple voltage, and that is not good, right. That is why we should use a filter right for the power supply, right, to have a good PSRR. Now, transient response, what exactly transient response means? This gives you an idea of how fast the op amp will respond to pulse input, right. So, rise time may be the time it takes from signal from 10% to 9%, how fast the op amp is, transient response. Then we talked about slew rate. What is slew rate? Slew rate is how fast the output can change, right. When you apply input signal, how fast the output can change with respect to input signal. This gives you an idea of the maximum frequency and amplitude signal that op amp can handle without any distortion, right. And then we have taken an example, and from the example what we found is that to operate without distortion, the way is to lower the voltage or lower the frequency, right. So, how does that work? How does that work? Either we can lower the voltage or we can lower the frequency. So, let us say let us see this example. Let us the LM741 output typically can only slew at 0.5 volt per microseconds. If you have performed the experiment, slew rate experiments, you will know that it is around 0.5 volt per microsecond. Now, if you have 10 kilohertz 10 volt peak sine wave on the output, the fastest point at which the voltage changes is at 0 crossing. The rate of change is dV by dt. So, 10 sine 2 pi into 10,000, right, 10,000 is a kilohertz. So, 10,000 T equals to 0.63 volts per microsecond. Since 0.63 volts per microsecond is above 0.5, there is a good chance that the 10 volt peak 10 kilohertz sine wave will have a distortion at 0 crossing, right. So, if you want to avoid this distortion, what we can do? We can either lower the voltage so that it comes around 0.5 volt per microsecond or below it, or we can lower the frequency, right. By lowering the voltage or frequency, we will see that the rate of change dV by dt would be less than 0.5 volt per microsecond, right. So, again LM47 is considered as a slow op amp. However, you can get op amps with a slew rate in excess of 1000 volt per microsecond or 1 volt per nanosecond. So fast, right? Slew rate can be very fast. Okay. Then we move to next parameter, and this parameter is also mentioned in the data sheet, that is called bandwidth or gain bandwidth product. The gain is as a function of frequency for smaller signals. This means that with a 1 megahertz input, the maximum gain is 1. Actually, the gain is less than 1 because gain bandwidth product is defined as 3 dB point, right. We have seen why 3 dB, where the voltage drops around 0.707 of its original value. If the signal input signal was 100 kilohertz, the maximum gain would be 10. with a 10 kilohertz input the maximum gain would be 100 and so on, right. So, this is how the gain bandwidth product is defined, and the LM741 is considered again as a slow op amp, right. There are op amps available with a gain bit product of or gain bandwidth product around and over 1 gigahertz. So, what is another parameter? Supply current, the current drawn from the power supply when no load on the op amp, right. So, there are low power op amps available that runs on the less than 10 microampere. Usually the faster op amp, the power it requires is more. Faster op amp more power, slower op amp less power. Okay. So, this is all about your data sheet of the op amp. So, in this particular module what we have seen? We have seen that we have just quickly summarized about ICs, we have quickly summarized about the substrate, and we have seen characteristics of op amp as well as some realistic parameters and some characteristics or parameters that are listed in data sheet. Right. In the next module we will see some applications of op amp, and then we will move to actually implementing the circuits, right, using not only simulation, but like I said and I mentioned we will use kits to perform the experiment. All right. So, just go through this particular module and understand and make your concepts clear, because these concepts would be used in the following classes. Right. Till then, take care, bye.